my best. Yeah, you know, I almost tempted to take it, but I was like, I better not this time.
Did they come and sing?
Red.
Yeah.
It's always fun to think about.
I see she looks suspicious. What were you doing?
Ryan will just,
See, and you're hesitating to answer over too late.
what I was doing?
Yes.
Let me tell you in your ear. So wait, Dr. Bush, with logistics regression, is there, in the way we do have for like linear models, parametric models assessing, kind of are things statistically reasonable or a good model? I guess, are there those kind of hypothesis tests for logistics regression that assess reasonability of the model?
Yeah, it mimics very well, but
Very like null alternate hypothesis and just,
what you're gonna learn is that instead of a quantitative output variable y, you're developing a model for the log odds. And that's where the word logistic comes from, log odd, where the G comes from.
Oh, does it really?
Yeah, well, log, sorry. So, you're saying the log of the odds are linearly related to the predictor variable. And then from there, you can back engineer and get a model for the actual probability of something happening.
okay.
Yeah, when I first saw it, it was like, oh, this is really cool. And the math is really neat.
So will we cover any like non-linear regression?
Okay,
What
yeah,
does that
let's start-
look like?
No, let's,
that-
well, that was a special thing that I gave to Ryan.
Oh, no, yeah, just, okay.
So, yeah, let's start going over, I'll get you a syllabus next week, is, I kinda wanna get through the first night and see what you know, and, but, let's see, we're together for like 7 weeks, I think, probably 6 or 7, as soon as I count them up. So, what I'm supposed to do, and I will, is give a really efficient, let's use that word, overview of statistical inference. So we're gonna start tonight with, okay, sampling distributions. Okay, because all of statistical inference is based on sampling distributions. Okay, it tells you what the distribution is for. And we're gonna look at these parameters. Now, hopefully this should be somewhat familiar vocabulary. A proportion, a mean, the difference of two proportions, the difference of two means, okay? A variance, and the ratio, instead of the difference, the ratio of two variances. And we're gonna look at the sampling distribution of all of them. Okay? 1, 2, 3, 4, 5, 6 of them. And this is a proportion, a population proportion. And mean, difference of proportions, difference, mean, population variance. So once we do that, then next week we'll start estimating with confidence intervals. And I thought, and I've done this before, and I think this is the best way to do it. Okay? with confidence intervals, and we'll just build confidence interval for all of them, okay? So after a point in the lesson, I'm gonna be doing the same thing. After that, we'll do a test of hypothesis, but this week only for the ones that involve a single parameter, one parameter. Yeah, because there's a lot of stuff in a test of hypothesis. There's a lot of stuff. And then the next week, week 4, okay, we'll finish this list. 2 parameters. We'll finish this list. We'll do that, that, and that. All right. So there we've got an overview of what's typically in an undergraduate course. Then we can get into chi-square tests and ANOVA test, analysis of variance. Okay. And then we'll wrap it up with a treatment of linear regression. We can do that in the nights. That's pretty much the course. Ryan, would you agree that that's pretty much an overview of what's in undergraduate stats?
Checks out from what I've seen in Tierney's courses.
Was that?
Checks out from what I've seen in Tierney's courses.
Yeah. Yep. That's what we're gonna do. That's what we're gonna do. So yeah, but tonight, sampling distributions, and I want to just give you a real good understanding of sampling distributions. A lot of you have heard me talk about, the AP Stats course and program, and sampling distributions really bring a stats course to a grinding halt. It tends to be very elusive. So I've got some teaching aids tonight that are going to help. And gang, this is typical. I give some notes here, and they're also on our Canvas. Ahmed is part of us. He's away right now. Okay, there we go. So again, so I'm going to start with a proportion, and then go to a mean, and I'm going to tell you all about sampling distributions. Let me, over here, sampling distributions. Okay. I want to focus on the conditions that come along with each distribution, as well as the characteristic, the shape, the center, spread. Okay. Center as measured by the mean, spread, standard deviation, and then using it. Using it. Let's use it. Yeah, put it to some good use. All right. I have a lot of this written out for you. Let's look at example 1. Okay, and what I want to do here, give me a second to pull some things up. I have a PowerPoint. I don't think I'll use it quite yet. Okay. I think I'll just pull up the notes. Yeah, we're looking for sampling distributions. Okay. So our opening example is this. A public health researcher wants to estimate the true proportion of mosquitoes in a certain region that are carriers of some disease. Mosquitoes carry diseases, but not all mosquitoes are carriers. Okay? So let's begin the way we always begin an inference problem, because the idea of inference is to make a claim, test a claim, or estimate some unknown population parameter. Right now we're focused on that one. Okay, the population, and the answer is down on the bottom. All mosquitoes in the region. Okay? Yeah. Good luck taking a census. Now, a census is when you are able to canvass, to get data from everybody in the population. We wanted to know the true average age of all full-time faculty at Duquesne. That wouldn't be that hard to do. I can guarantee you human resources can do it in a New York City minute. They got a database, you know, they've got all the faculty members. They can search on full-time faculty. There's your list. There's their birthday. I guarantee that's in their database. And figure out their age. I can do it to the exact day. Okay, I'm not going to do it to us, but it wouldn't be that hard to do, and that would be called a census. Yeah. But here, all mosquitoes in the region? Yeah. Good luck with that. Now the parameter, okay, is P, that's the first on the list, a population proportion. It's the true, honest-to-goodness proportion of mosquitoes in that region that are carriers of disease X, whatever that disease is. So what I'd like to do is I'd like to do a demonstration, a simulation, okay, right here. Now, let's assume a value for the parameter. Normally we don't know the parameter, but let's for the sake of this demonstration, assume that 30% of mosquitoes in the region are in fact carriers, exactly 30%. Now I'm going to go to a lovely simulation package, not StatKey, although not Statlet, but Statlet will do it. I like this one better. Usually I have to do it this way. StatKey block 5. StatKey block 5. Okay. Yeah, we're going to be using this a lot too. Right now, sampling distributions about, not today, well, not right now yet, a proportion. Going that way. All right. Now, so I'm going to take samples of size 20, 50, 100, and 250. Okay? I'm going to put my information over here. 20, 50, 100, and 250. I'm going to be taking samples, let's start with size 20. 20 mosquitoes. Now, what I have to do, the display is very small here, but I'm putting in the proportion of 0.30 right there. So it's like I'm reaching into this mythical virtual population of mosquitoes. Okay. I'm going to change my sample size to 20. Okay. I know it's rather hard to see there. So I click this, generate one sample, and it did. And it reached into this virtual population of mosquitoes, of which 30% have the disease. And it found 9 out of 20. 9 out of 20. Saying, well, that's not 30%. That's right. We call that sampling variability. It's not going to be exactly 30. You're going to get lucky sometimes. Most of the time, you're not. That's 45%. So that little sample of 20 mosquitoes overestimated the parameter. It puts a little dot right there. So I'm gonna do it again. I'm gonna do it again. I reached in, ooh, I got 7 out of 20. Still a little bit of an overestimate. Not as much though, 0.35, okay? We expect to get 6. And we'll get 6. No, we'll get 6 just by dumb luck. Oh, I just sampled a third one and that was also 7 out of 20. We've got 3 overestimates. We've got 4 of them, but the law of large numbers will catch up with us. 50%, woo! 13, got a bunch of overestimates here. We'll get one, there's one. 4 out of 20, 20%. So every time I click on that, it gets another sample of 20, it calculates the sample proportion, and puts a little dot there. But it's also tracking the mean, and again, it's hard to see, but it's 0.407, the average of all of these values. The average of all these values. And by the way, these are estimates. They are estimates. We call them point estimates. All of these are point estimates. Point estimates. And right now we're just dealing with the first one. And we call that p hat. And now we put a hat over something. We estimate it. I'm just going to keep going.
Professor, can you show like how did you start it, like putting the first like sample size?
Sure. The sample size goes right here. Okay, 20.
Professor, I'm not getting that sample size. Is everything in getting?
Let's see. Yeah, sure. Play all with that? Sure. All right. Oh, let's go back. You've got it on a randomization test. So let's go back. Yeah. Want that one right there.
Oh.
Yeah. So sample size of 20. 20. And we need the true proportion of 0.3. Right? Well, that's pretty cool. You know, you're doing it right there with me. Very nice, very nice. All right. So we want to fast forward this process, right? Now you can do one at a time, but if you look over here, generate 10 samples at a time. So here I am just banging on it, right? I could choose 100 at a time. Woo! I could do 1,000 at a time. I know you're just dying to see me hit that one. Okay. And now I've hit it a lot, so it's kind of needs to catch up with me. Yeah, it's getting angry with me. Now, this is a simulation of the sampling distribution. The sampling distribution simply is the probability distribution of a point estimate. That's all it is. We have simulated it. Okay? Now, the mean, I don't know if you can see that up there. Okay? I can barely see it up there, but I'm going to read it off the screen. Yeah, 0.300. 0.300. Ooh, yeah. That's the value of P, isn't it? Did I erase it? Yeah, I erased it. Yeah, that's the value of P. And that one's pretty easy to convince yourself of. We got overestimates, we got underestimates, and a lot of the times we were dead on. Dead on. Yeah. You know, the overestimating, underestimating are right where you're supposed to be. And at the end of the day, the overestimates balance with the underestimates, and we get 0.3. For those who've had stat theory, it's called unbiasedness, property of being unbiased. The standard error, you can consider right now to be the standard deviation. So right here, all right, this is from my simulation. Okay, I'm going to put mean and standard deviation. Okay. And by the way, I sampled, looks like about 13,000 samples. Okay. The mean is 0.3. The standard deviation is 0.102. Again, that number is keeping track of it. It's taking the standard deviation of all 13,517 values of p hat. Okay, but the shape, I don't know, Caleb, what would you call that normal, or does it make you a little bit nervous there?
Yeah, maybe.
A little skewed there, a little
Yeah.
skewed there, shake it. I agree, it's a little skewed there, a little bit skewed. Not much, but a little bit. All right, let's reset the plot and do samples of size 50. And I can do the same thing. I reach in, do one at a time. Let's see, what's the last one that I got? 15 out of 50. That's 0.3. Last one I got was 0.3. Do it a couple more times. Ooh, 22 out of 50. Okay, for an estimate of 0.44. That's an overestimate. But again, I want to fast forward a little. 10, 100. Okay, 100 works real well. Okay, there's 1,000. I wait for it to catch up. I think I'd be better off banging on the 100. Yeah. And once again, there we go. There we go. Let's get a couple. No, there's just a whole lot in there. All right. So, okay. The skewness that we saw before is not that egregious, not as egregious there. Okay. Oh, looks like I've got about 12,000 samples, good enough. And the mean is once again, okay, it's 0.3.
It's still increasing, Professor. It went 2,000 more, 40,000.
Oh, okay, thank you, yeah. And it's still 0.3, thanks. But the standard deviation, okay, almost got cut in half. Yeah, I know it kind of looks like it was the same standard deviation, but the program scales. Yeah, if I had the other one back, I think it probably went down to 0, probably as high as like 0.7. So, wow, that's good. That's good. So, very important property that as a sample size increases, the standard deviation decreases. And isn't that what we want? We like small standard deviations, don't we? Oh, yes, we do. Let's do 100. Okay, we're just going to jump right into the 1,000, 4,000, 5,000, 6,000, 7, 8, 9, 10. Come on. Yeah, we get 10,000. 8,009, 10. Okay, what do we got? Yep, gain is 0.300. Standard deviation, I expect it to be smaller. 0.046. 0.046. And finally, which is probably overkill at this point, okay, big old samples of size 250. Okay. Big old samples of size 250. And we see that the shape is approximately normal. So this is, in my opinion, is a great teaching tool for learning what a sampling distribution is. Are you looking at the sampling distribution? No. You're looking at an approximation of the sampling distribution. Yeah, anything based on a simulation, okay, will give an approximation, but a pretty darn good one. An exact sampling distribution? No. Yeah. And 10,000 again, 0.3 and 0.029. 0.3 and 0.029. Yep, as the sample size increased, the standard deviation decreased. And the mean stayed the same. The mean stayed the same. So yay, that is, observe the shape, center, spread of these four sampling distributions. We were kind of happy with all of the shapes except for the first one. Okay, so, yeah.
So, by this, like, if we observe this, we see that as we choose more number of, the sample size is more, the standard deviation reduces.
Exactly. You're going to find out why in just a minute. Yeah. You're going to find out why. I'll tell you why. It's in this box. Okay? Sampling distribution of a sample proportion. So consider a simple random sample, which the program was doing, size n from a population of size capital N, or it could be virtually infinite, with proportion p of success, p being 0.3 for us. But p hat be the sample proportion. Okay. Then, this gives all information about the sampling distribution. The shape, the center, and the spread. First, the center. The mean of p hat is p. The mean of p hat is p. Let's add that to the list here. Let's add this over here. So we're done with all of this. Okay? We're done with this. So we want the mean of the sampling distribution. We're going to denote that. The mean of p hat. Yes, that's the symbol for the mean, but it's of p hat. And this theorem says that it's p. But don't take the theorem's word for it. We saw it ourselves. Yeah, we saw that in the simulation. It actually physically averaged the 10,000 values of p hat, and it got 0.3. The standard deviation, ooh, the standard deviation. Standard deviation. We're going to label it like this, and it is p 1 minus p over n. N being the sample size. Aha! Well, Natish, that answers your question. Because as a sample size increases, since it's in the denominator here, you increase the denominator, right? 1/3, 1/5, 1/10, 1/100. You're going to decrease the fraction. Right. That explains that one. Yeah, that's why it happens. Now, let's do even something more fun. How do these numbers compare with what they theoretically should be? This one should be 0.3, 1 minus p, that's 0.7 over 20. This one should be at least reasonably close. Okay? 0.3, 0.7 divided by 100, and this one should be 0.3 times 0.7 divided by 250. That's what these numbers should be, or again, reasonably close. Let's find out. I'm going to go to my favorite little calculator. I'm going to go to Desmos, okay? And Desmos will help me out with that. Right. So I'm just going to use it as a calculator today. Square root of, let's put a placeholder here, okay? 0.3 times 0.7 was about 20, and that number is 0.102. Oh, that calculation is 0.102. That's what the simulation got. It's really, really important that you trust me that the simulation did not cheat and did not run to that formula. No, the simulation physically took the standard deviation, treated it as data, like 10,000 pieces of data, and it actually took the sample standard deviation. Let's see what it is for 50. How do we do? 0.065, okay? 065. Okay, technically 48. No, wonder, it only displayed it to 2 decimal. It would have rounded 0.65. Close enough. Yeah, close enough. I am not worried about that difference. Because again, these are simulations. 100.046. Oh, yeah, 0.046. 0.046, 0.046. And the last one, let's change it to 250. 0.029, 0.029. Yeah. Never fails me. Never fails me. Yeah. So that is a live demonstration of a sampling distribution. It's much better than me slapping up the theorems as here's the sampling distribution, here's the characteristic. No. You got to see it for yourself. Okay? Now, as far as the shape is concerned, as the sample size increases, the sampling distribution of the sample proportion becomes more approximately normal. Now, here comes the baggage. The baggage. The conditions. The conditions. All right. The conditions that must be met for this. Okay, for the shape to be approximately normal. We were a little worried about that first one. Okay, before you apply the theorem, you need to check what's called the large counts condition. Check that n times p is at least 10, and n times 1 minus p is at least 10. Wait a minute. So that first one, np, where the sample size was 20 and the p is 0.3, that's 6, yeah. I didn't pass the large condition, the large counts test. That one didn't pass. And we saw it, we were a little nervous about it, right? A little skewness in it. Yeah. All the others did. Yeah.
Question. Is that n times p being at least 10 a textbook statistics thing, or is that like actually come from, I guess I'm just curious for that 10.
I'll tell you, on the one hand, it's a little bit subjective, but where it comes from is the actual true to God formula for the variance, because technically you're always sampling from like a finite population. I mean, technically. And there's something called the finite population correction factor. But when you're sampling from a, I'm sorry, no, back up. I'm thinking of this one. This one is a little on the subjective side. Yeah. That's steeped in just looking at various simulations and see where the breakaway point is. But this one, is getting a 10%. Here's this one. This formula holds true as long as the population size is at least. There's a number missing there. I never noticed that. 10. At least. Can I fix that? I can fix that right here. I can. 10. Oh, back up. 10 times the sample size. And it's right there. And Ryan, that's where the finite population correction factor comes in. I can show you later. That's when we deem it negligible. Okay, so we'll keep that in mind. And this one requires a random sample. So our conditions, we're gonna refer to them by these easy to remember words. Random, okay? We call this independence. Okay. like for those who know probability theory, so that when you're choosing mosquitoes, you're doing it more like a binomial and less like a hypergeometric, where you're sampling from a finite population, and then large counts. Okay. This one, okay, again, the population size is at least 10 times the sample size. This one, NP is at least 10, and 1 minus P is at least 10. So that's our baggage. That's what we need to check. We need to make sure that those are satisfied to our satisfaction, right, before jumping in. So there we go. That is everything you need to know about a sampling distribution of a sample proportion. Let's put it to some use. Okay, again, I'm going through all of this pretty fast, so I like to write this out for you. Back to the mosquito, back to the jungle. 30% of mosquitoes in a certain area are carriers of disease X. This time, we have a random sample of 84. I'll tell you what, let's get on stat key. Be one step ahead of the problem here. I'm going to change it to 84. Oh, no. 84. It looks like there's some noise there right now. It's waiting for me to catch it. Actually, it's a little slow. Okay, yeah, we're up to 8,000. Actually, a little slow tonight. 11,000. Now let's do one more. 84. And I see a mean of 0.3 and a standard deviation of 0.05. Okay, again, really wish the display were larger for you guys. All right, 0.300, 0.050. All right, well, let's find, that's what it was in practice here. Let's find out what it's supposed to be. Okay, so first the conditions, a random sample. Yeah, we took a random sample of mosquitoes, or as random as we're going to at least consider these to be a random sample. Yeah, for those who know sampling, by the letter of the law, a random sample. Yeah. Independent. It's reasonable to assume there are more than 840 mosquitoes in the region. Sometimes in my backyard, it seems like there's more than 840 mosquitoes, so yeah, I'm willing to accept that. And there's the large counts condition. Both of these quantities are at least 10. Yay! So, we have permission to proceed. And I'm going to get the parameters of the sampling distribution, the mean and the standard deviation. Run it through, run it through, run it through. Oh yeah, it's exactly 0.05. That's why I made it 84. Okay? Yeah, just like StatKey told me it would be. Now I sketched the sampling distribution. Nice normal curve. Okay. Send it to 0.3, and you go out 1, 2, 3 standard deviations to the left, 1, 2, 3 standard deviations to the right. Okay. Here's the title. It's a little wordy. Sample proportion of mosquitoes with the disease out of 84 mosquitoes. Yeah. You want a pretty good descriptor of what these numbers are. Yes, they're proportions, but a little bit more than that. They're the sample proportion of mosquitoes with the disease. In other words, in a sample of 84 mosquitoes, most likely I'll see between 20% and 40% as a sample proportion. Anything over 40, possible but not likely. Under 20, anything's possible. Yeah, a little less likely. And now, to calculate the probability. Now you don't have this on your handout, but it is available on the one that I uploaded. There's how to do it on your graphing calculator. Gang, we like a little program called Staplet. I'd like to introduce you to that. I'll show you Staplet. Just run to your favorite app. We're not using tables or anything like that. Nobody uses tables anymore. So, probability normal distribution. Again, the mean is 0.3 and the standard deviation is 0.05. Okay. And it does everything except label it for us. Yeah? And what we want, what did we want? We want the probability, okay, yes, there's a question on here. Oh yeah, find the probability that between 27% and 33% of mosquitoes, yeah, the sample proportion is between 27% and 33%. So I'm going to go up to this. I'm going to calculate an area. Down here. Oh yeah, between two values. 0.27 and 0.33. And calculated that area. Yeah, it located 0.27 and 0.33 and it's shaded in the middle. And that area is 0.4515. Yeah, 0.4515. So here, what I would write down here, the probability that P hat is between 0.27 and 0.33 is 0.4525. Yeah, about a 45% chance that you'll, 4515. A 45% chance that you'll see between 27% and 30%. And that's our first sampling distribution. That's our first one. Yep. All right. Now, everybody comfortable with that? With the language? Pretty good with that? Good.
Well, we'll check that one off.
Let's go to the mean now. That's the next on our hit list. All right. Let's go to the mean. Right. That looks like it's page 3. And I'm going to do this all over again, okay? So, this one I want to break up. Let's sample from a normal distribution. Now, that'll give me a little bit of time here. Okay, so, gotta go here, and got some data sets. Okay. This one's called battery lifetime data set. This one is a population of 8,000 batteries and their lifetime. Right. It's in a little file called battery data set. All right, I'm going to go over to stat key. Right. I'm going to go back to the main menu. And this time I'm doing a sampling distribution about a mean. All right, so I've got my own data. I'm walking in with my own data. Now, stat key has some data. I'm going to get rid of it. Replace it with my own. Okay. You are about to see my data. Right, come on, my data.
Where did you
There
get
it
it?
is.
Where did you get your data?
I made it up. I did. Yeah, I made it up. I mean, I made it up based on reasonable numbers, but I wanted a distribution that's approximately normal. I wanted one with some outliers. Now, I inserted some low outliers, and these are batteries that are like faulty, fizzle out. And a couple of that last a usually long time. Yeah, put a lot of work into that, they just said. I've gotten a lot of mileage out of it too. So there you can see that the distribution, the population distribution is approximately normal, okay? And here are the characteristics. There are 8,000 batteries. The mean is 1,000 exactly. That's the way I made it. And the standard deviation is 90 exactly. That's the way I made it. So, yep. Anybody touch that data set? It's got like 1 million copies running around. Let's get rid of all of this. Let's get rid of all of this. And we know all about the distribution of these batteries. Okay? The mean is 1,000. Okay? I think it's hours. Standard deviation is 90. Was it minutes? I don't know. I made it up so long ago. Yeah. Yeah, it's hours. Yeah, 90 minutes would be. There we go. So, we're going to pretend we don't know what those numbers are. And we're going to reach in, and once again, we're going to take samples of 9, 25, 100, and 250. Okay. 9, 25, 100, and 250. And once again, I'm going to keep track of the mean. I'm going to keep track of the standard deviation of my sample. So, I'll just demonstrate the, I want samples of size 9. Okay. And then I do have a little bit up there about sampling. I don't want to sample too much, right? Because it's destructive sampling. You sample 9 batteries, you can't put them back. No, that's it. I don't want to sample a lot of them. There's one sample of 9. There's one sample of 9. And in that sample, again, you can't read it, but it's 943. Minus 943 with a standard deviation of 84. So that's an underestimate. I do it again. I get another sample. That means the average of those 9 batteries, 1,063. 1,063 with a standard deviation of 78.84. Okay. So we had an underestimate and an overestimate. Let's get one more going. That's an overestimate, 1,038. Well, we know what we're going to do, right? We're just going to pound on these, and we'll take repeated samples from this population. Okay, pay no attention to the little spikies that you see there. Because what it's actually doing is putting them in little bins. Okay. I'm up to 8,800, 9,800. Let's do one more. Okay. So I've got 10,000 something, 313. The mean, the average of all those little means, okay, all those little averages, is 1,045.13. How about just 1,045? With a standard deviation of all of these 10,000 means of 29.851. That one I'll carry out. 29.851. Okay. All right. That was nice. Let's do it again. Reset the plot. Take samples of size 25. Oh, and by the way, that sampling distribution looked roughly normal. Yeah, it did. Remember, there are outliers in there. I see a slight skewness, nothing I'm worried about though, because we're generally concerned with what's going on in the middle. And again, this is an approximation. one more. Okay, the mean there is 999.914. 999.914. Yeah, I can kind of see that because this one obviously grabbed some of those outliers. Some of those samples contain a few of those really low outliers. Kind of drag things down ever so slightly. I'm not worried about it. And the standard deviation 17.981. Well, like before, you increase the sample size, you decrease the standard deviation. One more time. To 1,000, to 100, to 100. 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. 10,000 samples of 100 batteries. Oh wow, I got a mean of exactly 1,000. I don't know if you can see that, but it's 1000.000. And the standard deviation 9.023. Wow, that's actually really unusual. That's really unusual. I don't think I've ever seen it exactly 3 decimal places, 1,000. Okay, this is the one I really want to do. 250. Okay, 250. Okay. And the shape is approximately normal. As I get more and more samples, it's literally beginning to take shape. Okay, I'm seeing 1,000.033, 1,000.033, with a standard deviation of 5.635. Okay, so a live demonstration of the sampling distribution. Okay. Oh, by the way, down below, the population, I'm on page 3, the population consisted of all 8,000 batteries. The parameter is what we call mu, the true mean, true average lifetime of all the batteries. Okay. And I did my fancy little simulation. And what we saw is what I'm calling theorem 2. All right. An X be a random variable possessing an approximate normal distribution. Okay. My battery data, well, approximately normally distributed. Worked really hard on that. Okay. With a mean mu, so that you can subscript it or not. You know, these days I'm not subscripting it. And a standard deviation of sigma x. Suppose that the sample mean is obtained from a random sample of n observations of x, which we did. Then, same 3 things. The mean of x bar. Ooh, let's put them over here. Let's add to our little table here. First off, the point estimate is x bar. We want, similar to up here, we want the mean and standard deviation of x bar. Well, this theorem says that the mean of the sampling distribution of x bar is your population mean. Yeah, and I saw that. There's 1,000 hours here and here. Yeah, that was nice. Ah, but the standard deviation, a little simpler formula. A little simpler formula. It's the population standard deviation divided by the square root of n. Let me make that nicer here. That looks like a... There we go. Well, once again, let's see how those numbers compare with what they should be. What they should be for this one, 90 over the square root of 9. Oh, I know what that is. Square root of 9 is 3. 90 divided by 3 is 30. I got 30, and it was, now that's 29.851. It's supposed to be 30. I'm pretty happy with that. All right, 90 divided by the square root of 25. Okay, 90 divided by 5, that's 18. That's supposed to be 18, and it was 17.981. Okay. This one, 90 divided by the square root of 100, yay. That's 9.023, yay. And 90 divided by root 250, okay. Not good with my square roots of 250. All right, so let's that. The decimal's running around somewhere. 90 divided by the square root of 250, and it's 5.692. 5.69. Nope. 5.692. California. So there we go. A live demonstration of the sampling distribution. This is a thing for persistence. Not yet. I don't know it. All right. So let's put it to some use. Page 4, please. Page 4. So, once again, we're doing a production run of 8,000 batteries. We know the mean, we know the standard deviation. Let's find the probability that the sample mean lifetime is more than 1,020 minutes. Okay. Oh, sorry. Let's check the baggage. The conditions. Same here, random condition. Same here, independence condition. But the large counts was particular to P. Alright? This one requires that the sample population, which we'll call the parent population, has an approximate normal distribution. That it does. That it does. Okay? Nice. So now, I'm going to come down here, and we're going to address those conditions officially. Yep. A random sample of the batteries was selected. Oh yeah. That stack key program absolutely takes a random sample. All right. Up there, we're selecting 25 batteries. So that's 250, and there are more than 250 batteries. There are 8,000 of them. And we're told that the lifetime has an approximate normal distribution. So these conditions were random, independence, and normality. Okay. We get the parameters. The mean of X bar is the same as the population mean, that's 1,000. Standard deviation is the 90 divided by the root 25. Yeah. One of the ones we did over there, that's 18. All right. So, the sampling distribution of X bar has a sample mean lifetime. The sampling distribution of X bar, the sample mean lifetime of a random sample of 25 batteries, is approximately normal, with 1,000 and mean of 1,000 minutes and a standard deviation of 18. Okay. And there I sketched it. I'm going to do it on Staplet. Alright. I'm going to reset it. So mean of 1,000 and a standard deviation of 30. Oops. There it is. There it is. 1,000, 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left. Okay? And we want the probability that the mean is more, the sample mean is more than 1,020. So, in symbols, I want the probability that X bar exceeds 1020. And we're just going to have technology do that. That's the least of my concern. It gives a very lovely illustration of that. 1020 is right here. 0.2525. That is 25% chance. Or 25% of random samples of 25, that's a coincidence, okay, will have a sample mean greater than 1,020. There we have it. That is the sampling distribution of the sample mean, provided we're sampling from a normal population. I've got one more in this series. Let me take a little break here. One more. So I don't want to lose the momentum. Example 5. What happens if we don't sample from a normal distribution? What happens if we don't? So.
Use a different formula.
Yep.
No.
Yep. There's a
It's
different
not
condition. This is the cool part. This is the really cool part. So we got to get back into our data set. Yeah. Now I have a file. It's a little dated right now. I keep wanting to update it. It's going to show the same thing. It's for the 2017 NFL season. Okay. Yeah, so it's like 6 years old. Not to worry though. Come on.
I think you should, click on the new option, right?
Yeah.
Make new option.
I'm doing it.
Oh, it is download
It's
and
blocked.
Can you click on that, on the downward arrow? In the URL, on your right.
It's here. Yeah, sure. Have at it. He's really upset. Although I don't have to. I can reach into my files and. Oh, there we go. Thank you. Yay. Okay. Thank you. What you are looking at, as of it was the opening day. Thank you again. That was awesome. As of the opening day of the NFL season back in 2017, you were looking at the age of every pro football player who was on the active roster on that day. Okay, so that's our population. Okay, every NFL player in the 2017 season who was on the active roster. We're just going to say every NFL player. So, okay, let's go over to this. Let's go edit the data. Let's get rid of my battery data, all 8,000 of them, and replace them with the football players. Oh, you're going to love this distribution. What do you think? What do you think the distribution's going to look like in football? And I'm not a big football fan, just to be clear, but
I imagine it would be skewed to younger ages.
25.
skewed.
26.
Like, probably around mid-20s would be
Yes,
most of
they
it.
centered around mid-20s, but skewed in which direction? The skewed refers to the tail.
Yeah.
Professor, the problem.
Why is that?
There is one silly problem.
Yeah.
What you people call as football.
Oh, yes. Hey, I watched Ted Lasso. I definitely watched Ted Lasso.
That's a good one.
Oh, that's a wonderful show. Oh my gosh, that is so good. Yeah.
I didn't watch the new, they just put out the,
I'm still, I think, on season 2. I'm like spread it
Yeah.
out. I don't binge watch.
Yeah.
That's not true. But not that one. I don't binge watch comedies.
Yeah.
Oh, I blew through Handmaid's Tale. And Game of Thrones. Ta-da! There it is. It is textbook skewed right. It is textbook. Look at that. Like, woo! But yeah, you were absolutely right. You know, most of the players are in their 20s. We got some awfully old players at the time. Ben Roethlisberger was on that list. Yeah. Yeah, most of a lot of them are punters, kickers, and the like. They come out, they do that thing, they go back. I love this data set. It is so skewed. So we're gonna do the whole darn thing over again. 9, 25, 100, and 250. And this is the amazing part. So you know what I'm gonna do. I'm just gonna erase all of this. Oh, very important. What is the mean standard deviation? No, I did not make this data set up, of course not. But I data scraped it. The mean is 26.095. All right, 26.095. So you know in a skewed right distribution, the median would be less. Median would be less. 3.325, I'm pretty sure. 3.325, yeah, 3.325. Okay, let's do it. All right, sample size 9. All right, let's start banging on this. We'll get up to 10,000 each time. But look at the shape. Where did the skewness go? Oh, there's a little bit of skewness. There's a little bit of skewness. There's a little bit. But it's not near. You know, compare that skewness to the one in the corner there of the original data. It's not near as egregious. 26.10. All right, you know what's going to happen. Reasonably close to that. And a standard deviation of 1.107. Okay, let's clear it. Let's do 25. Okay. And again, little skewness there. There's a tail there. Can't deny that. All right, so far 26.085. 26.085 compares very well with that. Standard deviation is 0.659. 0.659. Couple of more to do. And next time out, I'm gonna eliminate one of these. I think 4 was the overkill. Again, never mind those spiky things. It's the way that it kind of handles the display. I think what's more important is that it's calculating the mean and standard deviation from the exact data. And if you think about what's going on, it's reaching in there. And so far we're up to 7,000, 8,000 samples of size 100. Right, 26.102 still compares well with this, with a standard deviation of 0.324. Okay. Oh, by the way, how many were there? Our population size is
1693.
Thank you. Better eyes than I have. 1693. Okay. And then finally, again, what this is starting to go away. Yeah, starting to go away with the last one too. I don't see that tail too much anymore. That's what large sample sizes do. They even things out. All right, 26.093. Pretty good there. And 0.196. So this is the first big deal here, okay? That when sampling from non-normal populations, we still have a normal distribution. Doesn't come without a price though. Because remember that those first couple, they were kind of itchy. So let's take a look at theorem 3, which is the central limit theorem. Actually, the central limit theorem honestly is this part. central limit theorem is this part. Because these two are carryovers from the last one. Okay, the mean of the sampling distribution is the same as the population mean. Yes, okay, provided you're doing a random sample. This formula still holds true. Let's just check it out because we can. Okay, over here, Desmos. Okay, so what do we have? 3.325, 3.325 divided by, first off, the square root of 9, 1.108, 1.108, not bad. The next one was 25.665, 665. Yeah, plus 0.66. Okay. 100.3325. Okay. And all right, 250.210. Now, oddly enough, that was the best one. Okay, that one not too bad, not that bad. We're kind of pretty here. Well, there's a reason. There's a reason. Let me show you. Let me show you. Okay, so this formula holds true so long as the population size is at least 10 times the sample size. Whoops. Whoops. All right, well, we're not too bad here. 10 times the sample size is 1,000. There's 1,693, but here, 10 times the sample size is 2,500. No, we're way over that. That was a bit of a difference there. Yeah, that's a bit of a difference.
Professor, I did not get that. It was that, like, why our formula did not work.
Sure. That gets back to Ryan's question, why the formula doesn't work. Because that's not the formula. That's not the formula, but it's close enough. The real honest-to-goodness formula accounts for the population size. Okay? It accounts for the population size. And you say, well, when the population is really, really big, and I can show it to you next week, and again, it's called the finite population correction factor. When the population is like really, really big compared to the sample, this is a really good approximation, which is most of the case, right? We're usually selecting people, animals, or things from a huge population. Happen to be for this one, on purpose, we're selecting from a finite and somewhat small population, because I wanted to demonstrate. So yeah, I think I'll make it a note to show you that formula, and why, and how this enters into it. Why 10 times the sample size? Why that? That will make that extra little factor go away. Okay?
Professor, if our data size would have been much bigger, like around 2,500 or like 3,000, we would have got the number.
Mm-hmm. Yeah, we would have been closer. Absolutely. So yeah, this example is really carefully crafted. Now, as the sample size increases, the sampling distribution of the sample mean becomes closer and closer to the approximate normal distribution. So before we apply this theorem, we have to check that the sample size is at least 30. Okay? We like this, but we didn't like the shape for these two, and especially this one. This one was still showing the skewness. This one, not that bad. This is not that bad. So these two didn't satisfy, by the letter of the law, didn't satisfy this. This one didn't satisfy this. The 100 looks good. We like the 100. This is just a really good example and a really good data set to point out those conditions, how they might fail us sometimes. Kind of a fun one. So now, watch the next page, then we'll take a little break here. Going. We're gonna now amend that last condition. It was formerly known as normality. Yeah. All right, let's keep going with this. Okay. This time let's select 50 players. That sounds like a good compromise. Okay. So find the probability that the sample mean age is less than 25 years. Okay. And let me couch this another way. Okay. If I bet one of you, Claire, I'll make you a bet. We're going to randomly sample 25, 50 players. Okay. If the sample mean, if the mean age is less than 25, you get $10. If it's more than 25, I get $10. Now that's the pretend bet. I'm not allowed to do it for real. Okay. But again, if the sample mean is less than 25, Claire gets $10. If it's more than 25, I get Claire's $10. Okay. We're going to find out if Claire should take the bet. Yeah. So, so let's see. We have a random sample of players. Yeah, we know that there are more than 500 players on that active roster. And 50 is greater than or equal to 30. Sample size is large. Okay, that's great. So here's our parameter. All right, well, now right now, Claire's reminded that the mean was 26. So, you know, she's getting the raw end of the deal because I'm saying if your sample mean is less than a number that's less than the population mean to begin with. So, you know, you can see it right here. There's the sample mean, and we said, okay, if that's the population mean, if the sample mean is less than 25, so, you know, I'm afraid of scamming you, but you knew that. Yeah, it's, because that little blue is the odds of you winning, and, but, you know what? Let's do it. Because we can. All right, I'm going to reset the plot. I'm going to set it for 50. I mean, there is a chance that you would win. All right, I'm going to press that button. It's going to reach in there and get 50 players, take the average. Okay? Again, the odds are overwhelmingly in my favor. Let's find out. Boop. Oh, well, it's 25.9. It's 25.9. Yeah, so I was expected to win, I did. But, so anyway, there's the mean, there's the standard deviation, there is the sampling distribution in context, sampling distribution of X bar, which is the mean age of a random sample of 50 NFL players, is approximately normal, the mean of that, standard deviation of that. Lovely little sketch there, okay. Again, since I sometimes actually use this for some of my AP workshops, that's how you do it on your TI calculator. Statlet is great, any app. And yeah, there's about a 1% chance. Yeah. Odds of Claire winning, you know, 99 to 1. Or my 99 to her 1. So anyway. We are done. The groundwork has been set. The other ones will go faster. Because now you know what a sampling distribution is. I'm going to throw in a little theory on these. They'll come in pairs. We want to talk about the difference of two proportions and the difference of two means, a single variance, and the ratio of two variances. But let's take ourselves a break. I'm going to check my phone and we'll
Right.
back. And,
You're calling us a new.
all right.
You're calling us
Ooh,
new.
let's see what's going on around here.
Jokes on you, players. Jokes on you.
Not funny.
Elizabeth, Claire.
That's new.
he ran.
I'm not gonna gamble.
I need to get the jacket. My jacket is.
Oh, it's in the office.
I just remember like I lost my card.
Need a snack downstairs.
Like, yeah, you want me to take the photo of that? And shoot. Next time you say as the loser, the joke will.
You're the loser.
Huh?
You're the loser.
Come on.
Wait, can I get into your office?
Bring something real.
We need a drink, a snack from the vending machine. Now I'm starting to get hungry.
Really?
What the heck? It all went away. Look what you did.
What are you?
Broke it.
Yeah, good way to show the middle one.
Don't get it.
That's really.
Yeah, dude, that's nasty.
Feel it.
Ooh, it
Feel it.
Claire was sitting one day, and me and Ryan were sitting, and we were like really having some good discussion.
Good.
And this girl came in, Claire came in, she talked a little bit, and we said, okay, yeah, whatever, like, and then she was going to her class, and she talked really sweet to us, and while going back, she said, okay, see you later, losers. And there was this professor who was about to take in the class. Did she really say that to you guys?
That's good. That's good.
I bet you Dr. Bush was. Dr. Bush,
Yes.
are you familiar with duck bowling? They have that back in the day.
Yes.
It's like,
Heard of it. It's
Mini-
big in Canada.
oh, is that okay? Or originated.
Yeah.
But it's like the pins are like smaller, and they
Yes.
have like strings on them.
Yes.
So like they get set up quicker, and it just it's
Right,
almost
you're
like
pulling the string,
yeah.
they set up.
But it's like it's more like skee ball, you know?
Oh,
Just-
see,
yeah.
there's another one, right, where the pins are smaller. One of the churches over in East Liberty had, what did they call it?
Yeah.
There was a different name for
There's a different
that
name.
one.
ball was smaller, it was like a big wooden ball.
Yeah,
Yeah.
that's something, yeah, that's, think what? That's cool.
Is that fucking too?
No, that's Italian. I forget. Poor
I was telling
Italian
Claire,
accent
there's a
breaks
place in the
me.
south side called Pins. It's a huge, like,
Pins
bar
Mechanical?
space thing.
Oh,
Yes,
Pins Mechanical,
Pins.
so cool.
Yeah.
Yeah, I've been
Yeah,
there
I've
before.
never heard of that.
Yeah, that's a cool bar.
Yeah, but it's more like fun for adults. There's like,
Yeah.
they have like a big old arcade thing.
That does sound like fun. After all, I grew up on the Jersey coast, and
Yes.
I know what,
Yeah, they,
hey Caleb, do you have the take home?
Yeah, yeah.
Okay. Oh, great, super. Other thing is that assignment 4 that you sent me the program for, the program is really interesting, but did you turn in the actual thing with the answers and everything?
I don't think I did.
Okay.
Would you like me to?
If you can get that to me in that.
Yeah.
That was kind of a big one.
I just realized I don't. I didn't know if I zipped it for you either.
Oh, I got it.
Did you get the whole?
Yeah.
Okay.
Yeah.
And
And
then
there's some of the answers on there, but not all of them, so. Let's see when I talk back and forth.
Okay.
Yeah, cause I can hold on the.
Yeah.
on the-
No, I can do that tomorrow. I'll look.
Okay.
And get the rest of those to you.
All right.
Question, Dr. Bush, I guess for our purposes with this side of the things we're looking at, does it not matter the covariance term? In terms of when we're adding a linear combination of random
Sure.
variables?
Because we're gonna assume that x1 and x2 are independent.
Okay,
Covariance
just
term
for
is
this.
0. And that is why, okay, we will require 2 independent random samples. Yeah. All right. Wait for Natisha to get back. Well, we're gonna lop off the next 2. I'm gonna tell you all the theory that you need to know. Okay? That theory being that the variance of the sum or difference of 2 independent random variables, x1, x2, x1 plus or minus, x2 is the variance of x1 always plus, even if it's x1 minus x2, it's going to add to the variance. Doesn't matter if we add or subtract. Yeah. Because of course, it makes sense because if this were a minus, and if this number were greater, then you'd have a negative variance. we do is we're going to apply this simple little theorem. We're gonna get, well, first off, let's go here. If we want to estimate the difference between two population proportions, well, seems to me that a reasonable point estimate would be the difference between sample proportions. And if we want to estimate the difference of two population means, looks to me like a reasonable estimate would be the difference of two sample means. And now, yeah, you can show properties of expected value. There we go. Okay, that the mean of the sampling distribution of this statistic is centered right where it should be. Mm-hmm. And same here, but we want formulas for those two. And again, very easy from probability theory, that if x1 and x2 are independent, then the variance of x1 plus or minus x2, will always add the variance. So, let's apply that here. The variance of P1 minus P2 is the variance of this. Remember, the variance is the standard deviation squared. So I'm going to write P1 minus P2 over P1 minus P1 over N1, the first sample size, plus P2, 1 minus P2 over that sample size. That is the variance. Slide over here. I want the standard deviation. Here we go. I have derived it. Same with this one. On the variance of the difference between two sample means. All right? So that's going to be the first variance, okay, plus the second variance. The second variance. All I did was square each of those. So the standard deviation, just take the square root of that. Done. Done. From that simple little theory and what I established up there, we get the other ones. You get the other ones. Mm-hmm. So let's swap those two off and see what they're all about. Okay. So this one. Suppose I bring in 2 bags of M&Ms. 2 bags of M&Ms. First bag is 35% red M&Ms. The second bag only has 25% red M&Ms. Okay? Wow. Now each bag contains more than 1,000 M&Ms. Okay, you know why that's there. We're covering our bases there. Using a paper cup, take a random sample of 50 M&Ms from the first bag and only 40 M&Ms in the second bag. All right. And we're going to get P1 hat minus P2 hat be the difference. We always have to put bag 1 minus bag 2 to tell us what direction the difference is. The difference in the sample proportion of red M&Ms. So 50 M&Ms sampled from the 35% bag, 40 M&Ms taken from the 25% bag. Okay. So what we're going to do is sketch the sampling distribution. First find the condition, check the conditions, and see what the probability probability is that the sample proportion, the difference between these two, exceeds 15%. So here we go. Random samples of M&Ms were selected. We know that there are more than 10 times the sample size, 500 in the first bag and 400 in the second bag, so that each bag has at least 1,000 M&Ms. Large counts is a bit of a pain. There it is for the first bag. Okay, and here it is for the second bag. But they're all, well, that one was tight. That one was tight. That one was tight. We made it. We're going to keep going. The parameters, the difference of the true proportions, 10%. Now for the standard deviation, just plug them in, crank them out. Yep, plugged in 0.35 for P1, 0.25 for P2. Notice those sample sizes. Crank them all without, and that's 0.09611. So, woo! Sampling distribution. P1 hat minus P2 hat, which is the difference. And bag 1 by bag 2. Of the sample proportion of M&Ms that are read from random samples of 50 and 40 respectively is approximately normal with a mean of 10%. Expect that difference to be 10%, sure. First one hit more M&Ms in it, more high proportion. And with a standard deviation of roughly about 10%. Now, because the difference could go negative. There it is, there's my sampling distribution. There's that standard deviation. And now I just want sampling distribution P1 hat minus P2 hat. Right? And again, you can go to your favorite app. Right? There I am doing it on the TI calculator. And I get about 0.3. You want to see this? Graph 0.15 is it's roughly right there. It's roughly right there. And that's about 15%. Yeah, that's about 15%. And that's how you do a sampling distribution for the difference in two proportions. The formulas are just messier. That's all. But they come from a very simple little theorem from probability theory. Let's do the same thing for a mean. The same thing for a mean. Okay. This one, sampling distribution of the difference of two sample means. Based on information from the U.S. National Health and Nutrition Examination Survey, the heights of 10-year-old girls follow a normal distribution of about 56.4 inches and a standard deviation of 2.7, where the heights of 10-year-old boys, this is true, well, 10-year-old boys are a little shorter than the girls, a little shorter. It's 5.7 inches and a standard deviation of 3.8. Now, when you take independent random samples of 12 girls and 8 boys, small sample sizes, we inspect the conditions to find and sketch the sampling distribution. We're going to have to strip this up as girls minus boys. Sample means height of girls minus sample means height of boys. And we're going to find this. What is the probability, even though the girls on average are taller than boys, look what that's asking. That's, in essence, asking, what's the probability in these two samples that the average height of the girls in the sample is less than the average height of the boys? It's not supposed to happen. Not supposed to happen. On average, the girls are taller than the boys, but not by much. But it could happen. Right? If we know that the probability is less than half. All right, so first off, the conditions. independent random samples, so yeah, we gotta be independent random samples, okay, of boys and girls were selected. I don't even have to say how many. We are quite sure that there are more than 120 girls and 80 boys in whatever population we're sampling from. It's really the population of all 10-year-old girls and boys. Normality or large samples. Ooh, we gotta go with the normality. And yes, distribution of heights for boys and girls independently are roughly normal. Yeah. So great. So the mean of the difference between these sample means is the difference between the mean height of the girls and the mean height of the boys, and that's 0.7. On average, the girls are 0.7 inches, 0.7 of an inch taller than the boys. Standard deviation, there it is. There's your individual standard deviations. Don't forget to square them. 12 and 8, 1.553. All right. Let's do it. Let's sketch it. There's a formal statement of the sampling distribution right there. Okay. Sampling distribution of x bar g minus x bar b. Okay. Is approximately normal with a mean of 0.7 and a standard deviation of 1.533. So there's my mean of 0.7. It doesn't take me long to get into the negative region. There's 0 right there for the difference. The blue, as we suspected, it's less than 50%, but it's not small. It's not small. The blue is the probability that the average height of the girls in the sample is less than the average height of the boys, right? And again, you just go to your favorite app, okay, and just put that in. Obviously, I did use StatQ with that. I get 0.326. There it is on the TI calculator down there. How'd that happen there? Yeah. So there we go. So that finishes off these two. Okay. And now these, which are traditionally not done in the first semester undergraduate stats course, but we can do those. Okay. So before I get to those, let me tell you how evaluation and assessment will go and all that. Towards the end of each class, starting with next week, as opposed to the last class, we had these hand-in assignments. And they were really, really difficult. I don't perceive these as really that difficult. But we're gonna have, I don't know, call it what you want. At the end of each class, just one problem for you to work, one or two, completely open book. And if you want some practice, I've got some practice exercises for you. And I think, yes, the answers are attached. So again, completely open book, you can use that, but basically I'll pick probably next week one or two of them. Probably one of them from start to finish and the other one maybe part of it. I'll do like the conditions. Okay. And then towards the end we'll have some sort of a larger thing. Regression, yeah. That one's really key. So anyway, let's take a look at the last two. All right. A sample distribution of a sample variance. So, probability theory tells us when random samples of size n are taken from a normal distribution with a variance sigma squared, that the sampling distribution of this statistic, sample size minus 1, sample variance, divided by the population variance, we'll have a chi-squared distribution with n minus 1 degrees of freedom. So this one I'm going to show you on Statlet. Here's our exercise. Suppose that in a population of 8,000 batteries, I'm back to the batteries, yep. The lifetime has an approximate normal distribution, which it did, of 1,000. That's supposed to be hours, yeah. That's supposed to be, I know it said minutes somewhere. I'm gonna change that right here and now, if I can.
And 90 or
Yeah. Hours.
100.
Yep. Right there. Okay. We're gonna sample 25. We're gonna find the probability that the sample standard deviation is more than 100 hours. It's more than 100 hours. The true standard deviation is 90 hours. We're gonna find out the probability that the sample variance is more than 100. So let me write down what we need. Okay. All right, find the probability that sample variance exceeds, okay? Actually, the sample standard deviation. So the sample variance must exceed 1,000 squared. That's what we want. Now, this is a chi-square distribution. So let's see, what I sampled 24. Okay. So what I have to do to both sides, all right? I'm going to write this n minus 1s squared, but over here I'll write the 24. N minus 1, 25 minus 1 is 24. Okay? Divided by the population variance, and that's 90 squared. That's what I have to craft it there. This is a chi-square random variable, and that, do I have a value for that? Yeah, I build it down there. I build it down there. I thought I did. That value is 29.63. 29.63. And this has 24 degrees of freedom. So I'm going to run over to, I'm going to go to the menu, Statlet. There's chi-square. All right. And, right. So area under the curve, 24 degrees of freedom. Yeah, I'm sorry, the folks from last term, it dawned on me that, see, in the other class, in the regression class, we use Statlet constantly. You're seeing this for the first time, right? I didn't use Statlet for anything, yeah. Okay, let me just back up a little. Let me back up. Statlet, S-T-A-P-P-L-E-T, Statlet. It actually is a wonderful series of applets. And let me go to the main menu. There's the main menu. Okay, does a whole bunch of great stuff. The ST. So anybody who had AP Stats, I think I asked this. Did you use the Flamingo book? Did anybody use the Flamingo book, AP Stats? Okay, that's the one I consult for. And the authors are Starnes and Tabor. Darren Starnes and Josh Tabor. ST. That's what the ST stands for. ST applets. Starnes and Tabor applets. And they accompanied the book but as generous people they are, it's free. They put it out there. They put it out there. And there's a whole lot of cool stuff that it does. In the other class, we've been using this menu up here, and we will. We're gonna be using that menu. Right now, I use the normal, and I'm gonna come down here, I'm gonna use the chi-square applet. Yeah. So I'm just gonna click on the applet, and I want a chi-square distribution of 24. And it gives it to me. You see a little skewness there, a little bit of skewness. Yeah, for really low values, degrees of freedom, it's got a lot of skewness. And I want the area to the right. It gives me an option. Do you want the area to the right of a value, the left of a value, or in between two values? Most of the time it's to the right. That's why it defaults to that. And that value that I want is 29.63. We can already kind of eyeball it. 29 is about right there. Well, it's got to be a hefty probability, 29.63. Yeah. Calculate the area. It did 0.1973. Yeah. There's our probability. Around about a 20% chance. Around about a 20% chance. So yeah, it just dawned on me. I'm so used to doing stuff with it, I forgot that you guys didn't use it. It's the other group, which they use that as well. Yep. So there we go. There it is on the TI calculator. Showing you where to go. And one more. The ratio of two variances. The ratio. We don't test for the difference of them. We test for the ratio of them. Yeah, that's what the theory says. So, from probability theory, okay, if you have two independent random samples, that one is a chi-square. That one is a chi-square. They are independent of each other. This one carries a certain degree of freedom, n minus 1. This one carries a degree of freedom, n minus 2. And the theory is that the ratio of two independent chi-square is an F distribution. An F distribution. And an F distribution carries a pair of degrees of freedom that are called numerator and denominator degrees of freedom. So, last one, all right? Pretty generic here. I just made this generic. All right. Suppose we have a random sample of 9 observations taken from an approximate normal population with a standard deviation of 5, and 11 observations taken from an approximate normal population with a standard deviation of 4. Okay. We're going to find the probability that the ratio of the two exceeds 5. Ratio of the two sample standard deviations, actually, the ratio of the two variances exceeds 5. Okay. Let's see, the ratio of the population variances, that would be 25 to 16. So yeah, it's pretty likely there. Let's find out. Let's find out. Right? So the same conditions do apply. You've got to have a random sample, okay? And then in this case, they've got to be random and independent. All right? The exercise states that, yeah, we're good enough so that the independence condition is satisfied. And each sample is selected from an approximate normal distribution. Yet that one is actually real important for this particular sampling distribution. So, I'm going to start with this right here. This is the thing that has an F distribution. So, all right, the N1, and 1 minus 1 is 8, okay, over 25, and I'm missing an S1 squared. I actually knew that. Just didn't type that in there. Okay, here, 11 minus 1 is 10, divided by that, okay, and there's my S2 squared. So that my number's reduced to 64 over 25. That's the thing that has an F distribution. Okay? So, variances have a lot of play to them. A lot of play. So, going to the original problem, find the probability that the ratio of the two variances exceeds 5. Well, this is the thing that has the F distribution. So I got to multiply both sides by 64 over 125. Okay? That becomes an F, and that becomes 64 over 25. And the 25 is divisible by 5. Now, let me go over to Staplet. Let's see. The degrees of freedom were 8 and 10. The sample size is 9 and 11, so it's 8 and 10. Let's see. Okay. Go back to the main menu. There's a lovely F distribution right there. See, it's setting me up. 8 and 10. Oops. 10. Yeah. Woo! There's your F distribution. Okay. What was my, well, I've got a copy right here. The number I wanted, okay, is, yes, I have to do it, here, yeah, I don't have that part in there now. And the number I want is 64 over 125.
25.
2,
Yeah.
5, 6.
What is that? It's
64 by 25.
Yeah, 64. And I think I need it as a decimal. Okay, so basically, all I have to do is multiply 64 by 4, and it would be 2.56. That decimal is 2.56. So, to the right of a value, 2.56, calculated the area, 827. Yep. So 0.0827 as a probability. Not that likely. There it is right there. But the picture, yeah, a copy of this is in our canvas type thing. So, and again, there's how you do an F distribution on the TI. Again, not typically done at an undergrad level. Stats 2, I do it when I do a Stats 2 course. Although, usually, when you do problems with sampling distribution, you just jump right to the tests. So, we've laid the groundwork for next week, where we're going to learn about confidence interval. We're going to use all of this stuff. We're going to go to confidence interval, we're going to go right down that line, okay? And we're going to build a confidence interval for P and mu and P1 minus P2 and mu1 minus mu2, yep. And this, and we're not going to do that. We're not going to do that. That's not typically not done. But we are going to do it when we do testing. So, all right, I'm done. I'm done.
So this is a fun one. Question, Dr.
Yeah.
Bush. Is there not a point estimate or mean and standard deviation parameter
Oh, I'm sorry.
for those
Sure.
lower
Okay,
two?
sure. So the tween estimate, right, the tween estimate would be S squared, and this would be S squared 1 over S squared 2. But we generally don't do this because we're not here, 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 and here. We're using the normal distribution. And you know how that goes. Take your number, subtract the mean, divided by the standard deviation. But we're using chi-square and f. Now, they do carry, of course, their distribution, so they do carry a variance. But yeah, we tend not to include that on the list because it's kind of irrelevant. But you're right, those are the point estimates. Yep. So, all right.
And then presumably the standard deviation will just be square root of s, square root of s1 squared divided by s2 squared, presumably?
Over here? The mean, well, again, since these are skewed, yeah, we'll just list this as not applicable. They exist, but they don't feed into our sampling distribution. Yeah. And again, because it's skewed, instead, we're looking at the whole distribution, chi-square. And we're building that weird thing that, n-1 s squared over sigma squared has a chi-square. That's what we're working with.
And the F distribution is always from 0.
Oh, great
yes.
point. F
Yeah.
and chi-square, always
Yeah.
from 0. Chi-square. Always can't be less than 0. And since an F, and I don't know if you do this, since the F is the ratio of two chi-squares, it's the ratio of two things that have got to be positive, so that one starts at 0 as well. All right. Yeah, I'll stick around if there's anything. Glad to meet our new folks here. Glad you were comfortable with everything. Great. Yeah, you've had steps before. This is going to be a refresher of everything. What programs are you in?
Pharmacology.
Farm, yay!
Same pharmacology.
Farm. So the other class, I've got,
I know.
yeah,
Yeah, my colleagues are taking.
the regression class, the
Yeah,
modeling
yeah,
class.
I know. Yeah.
So you know some people in there.
Yeah.
Okay, great. Hope they're happy. I'm going through they had a take-home exam, so I'm going through their life. I didn't get to see them on Tuesday because
Yes.
it was one of those goofy Monday schedule on Tuesday,
Right.
or Friday, or whatever they call it. Fridays are weird. All right, end of a long day. Did my 62 bike ride though. So we made it up, because the ride was canceled. We found out Friday that the ride was officially canceled. Or did we find out Thursday? Did we find out I forget. It was in Delaware,
Okay.
but with the rain, there was freaking rain.
Yeah, that weekend.
But my buddy and I said, well, we can't cancel the hotel, it's too late. So, we're gonna go.